Hello, this is Mr. Craig, and this is quiz number 2 for period number 5. Let's go ahead and get started here. Questions 1 through 4 refer to the aqueous solutions containing a 1-to-1 mole ratio of the following pairs of substances. Assume the concentrations are 1 molar. Select a one-lettered choice that best fits each statement. A choice may be used once, more than once, or not at all. Alright. So what we have here are 5 different solutions, and these things are mixed together. Actually, I want to go through each one of these and help identify what each of these would be. Now, I wouldn't recommend what I'm about to do if you're pressed for time and you're taking the AP exam. But for the purpose of understanding what these solutions are, this is a great question. And it was asked, I think, back in either 2002 or 1999. So, good question. I wouldn't be surprised if they asked something like this again. First thing we need to do is look at A and ask ourselves, well, what is sodium hydroxide? Well, sodium hydroxide is NaOH, and ammonia is NH3. Now, when I say what are these, make sure that you understand that sodium hydroxide is a strong base, where ammonia is a weak base. So we have a strong base with a weak base, okay? With a weak base. Okay, not the correct way to abbreviate that. All right, and then in letter B, we have sodium hydroxide, again, NaOH, and hydrochloric acid. Now, what do we have here? Well, we have a strong base with a strong acid. Okay, and again, these are just solutions, so at least we can identify what these are. And then in C, we have hydrobromic acid with potassium bromide. So hydrobromic, is that one of our 6 strong? And we have hydrochloric, hydrobromic, hydroiodic. So absolutely hydrobromic. And if you're not sure, take a look at the periodic table. So hydrobromic is a strong acid, and potassium bromide is actually conjugate of a strong base with the conjugate of a strong acid, which is just a salt. So it's potassium bromide's pretty worthless as a, well, I won't say what these are. And then sodium acetate with, acetic acid with sodium acetate. And let me go ahead and draw an arrow for that. So we have acetic acid, and make sure that you can write this. Acetate's one of our 10 polyatomics that we have to have memorized. And what is it? Sodium acetate. Okay, so C2H. Sorry. Okay. Alright, so what we have here is we've got a weak acid, and we've got a salt where we have sodium and the acetate. So we'll talk about that here in a moment. And then the last thing, methylamine and methylammonium chloride. Well, we've got something kind of unique here. We have something that we're not quite familiar with, but do realize that we have hydrogens on the back of this. And we haven't had organic chemistry, but do remember earlier on in the year when I said, when we were talking about acids and bases, if it ends in hydrogen, you're looking probably at a base. And then what we actually have is, we have a root compound very similar to this, except there's one small difference. There's 3 hydrogens at the end. And then we have the chlorine. So we actually have a conjugate of this thing, whatever that is, and a conjugate of a strong acid. So if you have a conjugate of a strong acid, then that means that you have a common ion encased within of this thing. And if this has one more hydrogen than this, then we're probably looking at a conjugate acid here. So some kind of conjugate acid. So identifying those with that's a conjugate acid, that's pretty safe to say that that's a base. Alright, so let's answer number 1. It says a buffer with a pH less than 7. Alright, first and foremost, what makes up a buffer solution? Well, a buffer solution, first and foremost, is something that can resist a large change in pH, whether you're adding a strong acid or a strong base. Okay? So first and foremost, and I'm using that term a lot here, you will never ever have a strong acid or a strong base within a buffer, because that's what the buffer system's trying to do. It's trying to regulate when a strong is added to the solution. So looking at sodium hydroxide, there's our strong base, so A is out. Looking at B, again, another strong base, so that one's out. Hydrobromic acid, again, we said that that was a strong acid, so A, B, and C are out for number 1. So now, since we're looking for a buffer with a pH less than 7, does that mean we're looking for an acidic or a basic type of buffer? Well, we're looking for an acidic type. So since we have acidic acid and the sodium acetate, I guarantee you that if you were to go through, hopefully you'll get a titration question in 2011. I'm hoping. When you do your pH, I guarantee it'll be on the acidic side. So number 1 has to be D, because you have a weak acid and it's salt. Okay. Buffer solution with the pH greater than 7. So flipping that over, we already went through and said A, B, and C can't be a buffer, and if we already said D is a buffer system for an acidic solution, then we have to focus on E here. And E actually does have a base, and we don't know it by name, but we know it because it's not one of our strong bases. Okay, make sure that you know your rules for your bases, which again state that we're going to look in group 1 from lithium on down, and then in group 2 calcium on down for with hydroxide. Those are your strong bases. Well, in this case here with the methylamine, we do not have, let me erase the acetic acid here and the sodium acetate, get rid of some of those, sorry. Alright, so with the methylamine, we do not have a strong base in this compound here, okay? And we actually have a conjugate ion. We don't need to know the name is a conjugate ion, but we do recognize that it has one more hydrogen. So letter E is our buffer solution that has a pH that's greater than 7, because it does behave like a base. Alright, number 3, the solution with a pH of 7. Okay, now going back, let me erase that. When we look at a buffer solution or a solution that has a pH of 7, not a buffer solution, we have to have equal volumes and the equal number of particles. Okay, and it has to be a strong with a strong. So in this explanation here, it says that we have a 1-to-1 mole ratio and the concentrations are 1 molar. So what that means is, for this answer here, I need to find a strong acid with a strong base. We identified that in letter B earlier on at the beginning. Okay. Number 4, the solution has the highest pH. So if we're talking about high pH, we're talking about something that is basic. So we need to find something that has a base with a base, and that was our explanation for A. So you have sodium hydroxide, which is a very strong base, and then we have a weak base that's added to that strong base, so it just causes the pH to go up just a little bit more. So whatever water is within the solution, ammonia is going to rip some hydrogens off of that water to make the solution more basic. So a base with a base makes the solution basic. So it should be A for that one. Alright. Number 5, when 142 grams of KO2 with a molecular weight of 71 grams is allowed to react with 88 grams of carbon dioxide with a molar mass of 44 grams, what is the maximum yield of O2 with the molecular weight of 32 grams? Now, maximum yield again deals with stoichiometry. So the first thing we have to do in stoichiometry is, number 1, write a balanced equation. So looking at this, and again, the equation is not balanced. So that's our job to take care of that. We have 2 potassiums here. Go ahead and start it off with that. Let's see, so now we have 6. Definitely need to have an even number of oxygens since I have an even over here. So I'm going to quickly change that one. Get rid of that, put that back. So I need 2 because again I had an odd number of oxygen, so I need to make it even since I have an even and an even. So now I've got 4 of those. My potassiums are good. I need to balance out my carbons. Okay, so I believe I've got the same number of potassium and carbons on both sides. Alright, now let's look at oxygen. So I need to find out what number I should place in here. So I have 8 times 2 plus 2 times 2, which is 4. So 8, 12, and then don't forget about these guys here. So I need a 3 there. Alright, so we need 12 total oxygens on both sides. Alright, so there's step one, write a balanced equation. And if I were working this out, I probably would circle this and come back, because again, it's going to take me a little bit of time to do this. Alright, so the first thing we need to do, we are given a molar mass amount of this. We have 142 grams of that. Actually, we have, let's not do that. Let's be smart about it. Eraser. We have 2 moles of that. Oops. 2 moles of that. How do I know that? 142 divided by 71. And then I have 2 moles of carbon dioxide. How do I know that? 88 grams divided by 44. So I have 2 moles of each. And then it wants to know what is the maximum yield of... Okay, so it looks like it's in grams, so it wants to know how many grams of those. Alright, so limiting reactant. We don't need to do a limiting reactant step because we can look at the problem and determine which one's going to run out first. So if I have my KO2 and my carbon dioxide and I have 2 moles of each of these, I guarantee you I'm going to run out of the KO2 first. Why? Because I have a higher coefficient, so I require more for the reaction to go on. In other words, I will have leftover carbon dioxide because I'm not reacting as much. I'm going to react all my carbon dioxide, or my potassium dioxide, or potassium oxide, sorry. And that, boy, that is really goofy looking. I'm not even going to go there. This is a past AP exam question, so don't bark at me about how that's written. So that is, actually, as I look at that, that is really an ugly question. Okay, so we've got our 2 moles of KO2. Okay. And we're going to do a mole ratio. Okay, so we know who our limiting reactant is, so we're not even going to worry about that step. So we'll go right to the mole ratio. Step 1, write a balanced equation. Step 2, change what was given into moles. Done. We did it. Step 3, use the mole ratio to get rid of the units, or get rid of the units that we started with and go to the units that we're looking for, which in this case is moles of gas, oxygen gas. And then since it wants it in grams, let's go ahead and do that too. So in 1 mole of oxygen, we have 32 grams. Okay, it says that. So we don't have to do anything fancy there. Alright, so let's do some quick mental math here. 2 times 3 is 6 divided by 4. So 6 divided by 4. Okay, and then we're going to multiply that by 32. Okay, so we have 192, sorry. 192 divided by 4, so approximately that's going to be a little less than 25. I'm guessing A, which would be wrong. Like 50, sorry, 48. Letter B. Okay, I got to learn to estimate a little better. So the best answer here should be B. B, please. Okay. So I know that 50 times 4 is 200. That's what I was trying to do in my head. And so we're going to have a little less than that. So 5 should be letter B. Okay. And again, don't have to do all these steps. This would be something I would circle and come back to. Everybody can do stoichiometry. At least in my class. You guys better be able to. Alright. Number 6. Okay. K is greater than 1. What does that mean? Well, what does K mean? It means you have your products over your reactants, first and foremost. Alright. The equilibrium mixture will favor products over reactants. You better believe it. A looks good. Man, we may be done right there. The equilibrium mixture will favor reactants over products. Negative. The equilibrium amounts of reactants and products. No. The reaction is irreversible. No, it's equilibrium. The reaction will not occur spontaneously. This will occur spontaneously since it favors the formation of products. Alright, now here's the thing I need to ask. If the equilibrium mixture will favor the reactants over the products, K would be less than 1. Because again, reactants are down here, so that number is higher than this number. Letter C, the equilibrium amounts of reactants and products are equal. What would the value of K be if they were equal? K would be equal to 1. Not greater than or less than. They'd be equal. The reaction is irreversible. Well, I hate to say it, but equilibrium reactions are forward and backward. So if we have a K, value, then we have a reversible reaction. The reaction will not occur spontaneously. Oh yeah, this will occur spontaneously because when we look or try to remember back when we were doing our K is greater than 1, then that means that delta G is less than 0. Okay, so those are some concepts that we have to remember. Also, if it's greater than 1, then that means, yeah, it's making products on its own. We don't have to do anything with that. So the best answer for 6 is A. Alrighty, calculate the enthalpy of formation for N, notice, no 2 here, just N, in the following reaction. Now, don't forget, anything in its elemental state has a value of 0. Alright, so N2 has a value of 0. It's already made. We don't have to do anything to it to make it. However, N by itself, we don't walk around in nature and find N all by itself. So we have to do something to make N all by itself. Also, do recall that when we talk about enthalpy, it's the sum of the products minus the sum of the reactants. Now, this is a really easy problem because it says the heat of reaction is 945.2 kilojoules, and then the products, well, we have 2N minus 0, because again, our reactions have a value of 0, so this becomes pretty darn easy. So if we ignore that part and just divide this by 2, that will equal N. So whatever 945 divided by 2 is, I'm guessing D. Okay? And no, it would not be a negative sign because products over reactants. So letter D should be number 7. Yeah. All right, number 8. Half-life of a radioactive isotope is 15 hours. How many hours would it take for a 73,458.257 gram sample to decay to 1/8 its original mass? I'm going to come clean, guys. I actually made this mass up in the problem. I put that in there because I knew it would make you guys smile and make you happy. Do we actually care what the mass is? No. We care about this amount of time. That's the amount of life for 1 half-life. So that's equal to 1 half-life. So 15 hours. And it wants to know 1/8 of the original mass. Okay. So if we start off with 100%, and then we go to 50%, it's 1 half-life, there's 1. Then if we go from 50% to 25%, there's 2 half-lives. And then if we go from 25% to 12.5%, there's 3 half-lives. Now let's stop right there. Probably what I should be doing is not necessarily doing percents, but we go from 1 to 1/2, 1/2 to 1/4. Yeah, that's probably better. And then 1/4 to 1/8. There we go. Okay, so we've gone through how many half-lives to go from 1 or 100% to 1/8 or 12.5%. We've gone through 3 half-lives. So if it takes 15 hours for 1 half-life, total time better be this. Okay, so we're not dividing, and I probably could have been mean and put 5 hours there just to throw you guys off, but 45 hours should be the correct answer for number 8. Yeah, and I put on there, really, I made the mass ridiculous on purpose. Alright, number 9. Which of the following molecules has nitrogen in a more positive oxidation state than N2O4? Well, let's find out what the oxidation state is. The O4, each oxygen has a -2 charge, and we have 4 of those, so -8. So that means that if we have 2 nitrogens, then each nitrogen has a +4 charge. This is actually a very easy question. I hate to say it. So when we look at nitrate, it has a total charge of -1, nitrogens +5, each oxygens -2. We're done. Okay. So A. Here, the charge on each nitrogen would be +2. So no. Here would be +4. Same charge. Out. Here we've got plus 6 plus 3 there for our nitrogen. That's out. And then, ooh, a whopping plus 1. So no. Alrighty, number 10. Which of the following will occur spontaneously at low temperatures? Good question. Now again, be sure. Whoa, where'd my thing go? Alright, so be sure that when we look at this, that we know the. Ooh, what happened there? Hang on, it's got a mind of its own. Alright. Be sure that we know this. Oops. No, the correct equation is delta H minus T delta S. Okay, make sure we know that equation. You're going to use it enough on Monday. I want to make sure that you know it. First and foremost, if it's going to be spontaneous, delta G has to be negative. And if we want this to occur at low temperatures, what that says about the equation is that one of these is going to have a positive value. Okay, I would like for you to memorize this. If we have an exothermic reaction and our temperature is low, then what that's saying is I have a negative and a negative. Well, that means that the temperature has to be low so it's not so overbearing on the hydrogen, or I'm sorry, the delta H, the enthalpy. Because we have a negative sign here, we don't want the temperature to be so high that the back part of the equation overthrows the delta H and causes delta G to be positive. So the correct answer should be A. Okay, and know all the scenarios. There are 4 scenarios, and I talked about them in the other videos. And the reason why I put this on most of the quizzes, or a question like this on most of the quizzes, is because you're going to see at least 1, 2, maybe even 3 different reworded type questions like this. So that's why I want you to know the equation and become very familiar with this type of problem. And who's to say that this won't be on the free response as question 2 or question 3 in 2011. Alright. Number 11. Which of the following aqueous solutions would have a pH greater than 7? Greater than 7 means that we're looking at a large concentration of OH and a very small concentration of hydrogen. So strong acid, no. This is still an acid because ammonia, NH3, behaves as a base, and ammonium is a conjugate of ammonia, which acts like an acid, so it'll be low. HCN, cyanic acid, also acidic. However, we do have something very unique here. Whenever you see a question like this, I guarantee you they're going to give you a common salt of one of these weak acids. So here it is. So potassium cyanide will dissociate 100% because it's a strong salt, and we're going to form this cyanide ion. Well, you have to ask yourself, well, what's the cyanide going to do? Well, the cyanide will react with water, rip a hydrogen off of it, and you're going to form the cyanic acid and OH. So there's a contender. We've got something that's going to form hydroxide. Well, I can automatically rule out E because that's one of our 6 strong bases. So letter D is the best choice. Alright, number 12. What is the voltage in the following half reaction? In the following half reactions are combined in a galvanic cell. Remember, galvanic cell is always looking for the most positive charge, so it can be spontaneous. And remember that one of these has to be oxidized while the other is reduced. So it looks like we've already got, and both of these half reactions currently are reduction reactions. So we have to flip one of these, but we don't flip both of them. So what we need to do is we need to take a look at who is the most positive. Well, that one is positive. So we're going to leave equation 1 alone, and we're going to flip equation 2. So that'll change the sign from a negative to a positive 271. So it looks like A is our best option without doing any math. Okay, so again, voltage, if I were to actually write this out and balance the equation, okay, let me do that real quick. It won't do it because they both have 1. If we have to have a multiplier to balance out the number of electrons, remember, we do not multiply the voltages. We do not multiply the voltages. That's an intensive property. Alright, number 13. We have bonds and bond energies, and it says calculate the heat of reaction for the following equation using the information given above. Now remember, when we have bond energies, we're actually taking reactants minus products. So what we need to do is, since you're given bond energies, that's your heads up, start drawing some Lewis structures. So carbon monoxide, carbon wants 4 bonds, give it its 4 bonds. Okay. Chlorine, chlorine. And remember, if it's in group 7A, it wants to have a single bond. And then CO, Cl2. Hey, even though oxygen's written here, whenever we see carbon, always place it in the middle. So I'll have a double bond on that, and we will have 2 chlorines. Okay. So there's our structures. Okay, so let's do some math here. We have 1 carbon oxygen triple bond, which has a value of 1075, plus 1 chlorine. Is it 1? Yeah. 1 chlorine, which is 243. And then we'll subtract it by, we have 1 carbon double bond, so 728, plus 2 carbon chlorine bonds, which is 326. Actually, let's not do 326. Let's do it up here. So 2 times that gives me 752. Okay. Alright, so we have, and I'm approximating here. Hopefully I can go down just a little without revealing. Okay. So I've got a 0 there, I've got an 8 there, I've got a 14 there. Then I've got 8, 1, 3, boom. So I'm going to have a negative value. Negative, a little over, wow, is it 62? That didn't look right. Huh. I may have done some crazy math here. Yeah, I did do some crazy math. I think it looks... Alright, so I'm guessing B. Yeah, that is weird. Oh well. Okay, so, yeah, make sure you take reactants minus products on that. Alright, number 14. All the following are true statements concerning reaction orders except, and again, reaction orders, if you're doing a rate law, and hopefully you'll get an opportunity to do that on Monday. Rate law, again, looks something like this, where if you have a 1, maybe a 2, okay. So this is our rate, in other words, what the molarity is per second. K is a constant, and then these are each of our reactants with our designated order there. Alright, let's see. All the following are true statements concerning reaction orders except the rate of a zero-order reaction is constant. Yes. After 3 half-lives, a radioactive sample will have one... No. I'm guessing B right off the bat. Let's continue. If tripling the concentration of a reactant causes... If tripling the concentration of a reactant causes the rate of reaction to increase by a factor of 9 times, then the reaction is second order. Yep, that's true. The units for the rate constant for a first order reaction are 1 over time, and that's easy to do. So if we have rate, and I would not expect you to do this on the AP exam, so if we had this, and again, this is molarity, okay, so what we're going to do is we're going to isolate that guy all by itself. So rate is molarity per time, so we would have molarity per time, which is our rate, and then you'll have molarity. So absolutely, that's true. And then if doubling the concentration of a reactant doubles the rate of reaction, then the reaction is first order for the reactant. Absolutely. So 14, B is the best answer. 15, choose the conjugate acid in the following reaction. Okay, well, let's identify them all. Don't worry about just the acid. Alright, so we need to look at the before and after. So here we've got 3, here we've got 4. So if we have 3 and 4 hydrogens, that's definitely what we have to key off of. So this is getting a hydrogen from somewhere. So this is acting like my acid, that is acting like my base. To get the NH4 back to NH3, it has to give a hydrogen away. So this is my conjugate acid, and that's my conjugate base. So choose the conjugate acid, NH4. Okay, and remember, conjugates are always on the product side. So letter C. 16. The reaction is given. Which of these is the reducing agent? Well, let's find out what the charges are. Aluminum by itself, no charge. Iron, well, sulfate has a -2 charge, so iron has to have a +2. Aluminum is +3, sulfate's still -2, so sulfate's not doing a stinking thing. And then iron is 0. So reducing agent means that the thing is oxidized. So who is oxidized in this reaction? Well, looks like aluminum goes from 0 to +3. So the reducing agent, and again, agents can only be on the reactant side, is Al. No charge. Okay. Had the question been asking who is the oxidizing agent, then you would have chosen iron sulfate, not iron. Okay, that would be bad. Because again, even though the iron is being reduced here, the agent is the whole package. So the correct answer for this question is A. 17. 30 milliliters of a 0.3 molar solution of aluminum sulfate is added to 60 milliliters of distilled water. What is the final concentration of the aluminum ions? So we're looking for the aluminum ions. Oops, that's not the correct way to write that. Yep. Hello. Go back. Okay, aluminum ions. So the +3 is inside. All right, so we're looking for the concentration of aluminum ions. So let's find out how many moles of aluminum we actually have. So if we know the volume and the molarity, let's start with the volume. And again, we should know that 30 milliliters is 0.3 moles. Okay, so, or I'm sorry, liters. So we'll take our volume times our molarity, which is 0.3 moles per liter. And in every single one of these aluminum sulfate molecules, how many aluminums do we have? 2. Okay, so it's kind of like stoichiometry. All right, so we've got 0.03, which is 0.009, then times 2. So now we've got 0.018 total moles of aluminum. All right, so let's see, can I scoot this without revealing? Good. Okay, so to calculate my new molarity, I'm going to take my moles that I have and I'm going to divide it by the total volume. So I have 30 milliliters and 60 milliliters. So that's 90 milliliters, which is 0.09 liters. I like this. 2.0. Or 0.2. Sorry. Yeah, had I had 2 molar on there, I probably would have been a little more careful. Alright, so I know that that goes into that twice. Huh. Huh, okay. Thought it was 2 molar. Maybe I did something goofy there. 0.018. How's that 0.2? Oh, I see. My bad. It would need to be 0.1 and 0.9. Got it. Got it. My bad. Alright. Number 18. Determine the oxidation number of sulfur. Probably the best way to do this is get it away from everybody. We know that sulfite is SO3 with a -2 charge. So sulfur, oxygen, and the whole thing's going to be -2. I've got 3 of them, and each one's a -2, so -6. So I need to have something that adds up to -2, so I have one of those, so it has to be a +4. Okay. So again, probably probably you could do that without that by looking and saying, okay, well each oxygen's -2 and there's 3 of them, so a total is a -6. -6. I know the whole thing needs to equal -2. So what number am I going to add to that? So +4. Alright, and that's showing it a little longer and a little more complicated, which is fine. But just remember, go fast, but be accurate, please. Alright, number 19. Element iridium 200 is formed as a result of 3 alpha particles and 3 alpha and 2 beta decays. Which of the following is the parent element? So we're actually working backward on it. It says it is formed. Alright, so we have iridium 200, 77. So what I need to do is subtract from this amount. So my alpha particles, again, an alpha particle is a helium atom with a mass of 4 and 2 protons. So I'm going to put, since I have 3, I'm going to put a 12 and a 6 there, and I'm just going to make a question mark. And again, then I'm going to subtract it from 2 betas, and a beta is an electron, and it looks like that. So I'm going to have 0 and -2, and just a question mark there. Alright, so I want to make sure that these all add up. Alright, so 77 minus 6 gives me 71. Then minus a -2 means that I'm going to change it to 73. So my bottom is 73. So 73. Huh. Wait a minute. It's formed. My bad. Going the wrong way. Oh. Yeah, okay, so decays. I'm sorry, guys. I am having a phenomenal brain fart here. Alright, so we don't want to subtract, we want to add because it's the end product that we're doing. So 77 plus 6, there we go. So it's 83, and then we will subtract that by 2. Yeah, just subtract it by 2 instead of adding it. So our bottom number is 81. We don't have to worry about that anymore. Alright, and then 212. So 212, 81. Hopefully it's selenium. Or not selenium, but TL. So E. Good. Yeah, sorry about that. Got to read the question a little more carefully. Number 20. Which of the following elements is most electronegative? Again, looking at the trends for electronegativity, when we go to the right, the electronegativities increase. As you go down, they decrease. Okay, so we're looking for the farthest one that's up and to the right, and again, know that hydrogen has a value of 2.1, so hopefully it won't be in there. Alright, so most electronegative, aluminum, carbon's winning so far, aluminum and carbon, so aluminum's out. Iodine should be out, and sodium's out. Okay, so now it's down to oxygen and carbon. Oxygen wins, since it's a neighbor right next to the fluorine. So I would choose E in this one. Alright, and again, make sure you know your periodic trends. Question 5 and question 6 on the AP exam are going to deal with periodic trends and a lot of things that you do not get to use a calculator for. As always, I hope this video has helped, and keep studying, guys, and if you have any questions, give me an email. Send me an email.